Hello everyone. So in my part, I will explain to you transformers in big data. So transformers, what are they? Transformers, originally introduced in paper Attention is All You Need by Vaswani, published in 2017 by Google, represent a paradigm shift in deep learning architectures. Unlike traditional sequential models, transformers leverage a self-attention mechanisms that allows them to weight the importance of different parts of the input sequence. This architecture has gained immense popularity, particularly in natural language processing tasks, due to its ability to capture long-range dependencies efficiently. In the context of big data, the transformer's unique architecture becomes especially valuable. Its self-attention mechanism enables it to process and understand relationships within large and complex data sets. This adaptability makes transformers a powerful tool for handling sequential data in diverse applications within the realm of big data analytics. So before breaking into the transformers architecture, I will explain to you the self-attention mechanism. So the self-attention mechanism is a key component of the transformer architecture, introduced to efficiently capture relationships between different positions in a sequence. So as you can see in the image, the multi-head attention is a crucial component in the transformers architecture. It's composed of three linear layers and a scaled dot product attention layer and a concat layer and linear layer. So the scale dot product attention is itself composed by a matrix multiplication layer, a scale layer, an optional mask layer, and a softmax layer, and the final a matrix multiplication. So let's assume we have an input sequence with the tokens named. We have x1, x2, x3, xn. So each xi represents a token in a sequence. And we have also this QKV that you see in the image. They are for each token xi. The self-attention mechanism creates these three vectors. So for the Q, I represents the token's query vector, and the ki represents the token's key vector, and the value vi represents the token's value vector. So to calculate the attention, scores, we have to apply the formula, this formula. So the attention equals to softmax of q k divided by the root square of day k. So day k is the dimensionality of the vector k, all multiplied by v. So as you can see, the attention makes a weighted sum of values, and the weight is the a that you can see in the next formula. The a is the weight. And for the mask layer that you have, that I said earlier, that is optional. It's used mainly in the decoder part. It can mask some or hide some tokens that don't have a relation within sequence. So to make this step, we have to add a m to the formula, as you can see in the third formula. Let's move now to the transformers architecture. So as you can see in the image, the transformers architecture is composed by an encoder in the left and the decoder on the right. So the encoder-decoder structure, the encoder processes the input sequence, and decoder generates the output sequence. We have the self-attention mechanism that enables the model to weight different parts of the input sequence differently when making predictions. And we have also the positional encoding. They are added to the input embeddings to provide information about the position of tokens in the sequence. And the multi-head attention. So the model employs multiple attention heads in parallel, allowing it to attend to different aspects of the input sequence simultaneously. We have also the feed-forward neural network, which processes each position independently through fully connected layers. And we have also the add and norm layer. So the add is equivalent to an element-wise addition. It allows the model to learn residual connections, helping with the flow of gradient during training. So as you can see, we have two inputs for the add and norm. We have the input that is the output of the previous block, and also the output of the feed forward block before the add and norm layer. And we have also, and the norm is equivalent to a layer normalization to normalize the values across the feature dimension to have a great stability in the model training. So let's deep dive into the categories of transformers. So we have three categories, three types. The first one is the sequence-to-sequence model. So sequence-to-sequence models are the OG transformers, the well-known transformers. These were introduced in the original transformer paper. All the way back, sequence-to-sequence transformers models adopt a relatively straightforward approach by embedding an entire sequence into a higher dimension, which is then decoded by a decoder. These were primarily designed for translation tasks due to their excellence at mapping sequences between languages. So, for example, if we want to translate a sentence from English to French, the sentence will pass by the decoder to create an embedding. So, for example, the sentence "My name is Rashid" will be encoded to Goog Grok. Its embedding is Goog Grok, and this embedding will be the input to the decoder that will give us the result of the translation. So as you can see in the second image, we have an encoder and a vector that is the output of the encoder, and will be the input of the decoder. And decoder will give us the output results. Let's move now to the second type. So the second type and the second type is the autoregressive models, popularized by GPT, well known by GPT, generative pre-trained transformer, leverage the prior tokens to predict the next token iteratively. They employ probabilistic inference to generate text, relying heavily on the decoder component of the transformer. Unlike sequence-to-sequence models, autoregressive models don't require an explicit input sequence and are suitable for text generation tasks. They have gained immense popularity and exhibit versatility, with fine-tuning making them valuable for various applications, especially in business contexts. And keep in mind that these models are composed by only decoders. They don't have encoder in its architecture. So, for example, we have a sentence. This is a blog post that we want to translate to Spanish. So, as you can see, these models can generate the next token depending on the previous token and the context simultaneously. And this operation is on every step of the generation. And its architecture is composed by a masked multi-head self-attention that found in each decoder block ensures that the tokens generated at each time step are based only on the current token and the past output. And we have also the encoder-decoder attention. This layer enables the decoder to consider the entire input sequence from the encoder and the partially decoded sequence simultaneously. This assists in tasks that require understanding the relationship between two different sequences, such as translation between two languages. And the final type is the auto-encoding models. And these models, they are composed by only encoders. So they are specifically oriented toward language understanding and classification tasks, aiming to capture meaningful representations of input data in their encoded form. The training process of auto-encoding models often involves bidirectionality, which means they consider both the forward and backward context of the input sequence. By leveraging bidirectional encoding, these models can capture dependencies and relationships within the text more effectively. Additionally, autoencoders employ masking techniques to deliberately hide or corrupt certain parts of the input during training. This process forces the model to learn robust features and develop the ability to reconstruct and identify missing or corrupted information notable. So we have the multi-head self-attention. The encoder block is composed of only multi-head self-attention and feed-forward layer. And let's take an example. So, for example, we have a sentence here: Apple is a tech company, not a fruit in this, not a fruit in this context. So, if we have a traditional model, it will consider the word apple as a fruit because it's traditional models don't can't make the relationships between a word and the whole sentence. But at the other hand, with the auto-encoding models, we can make this relationship. So the model will understand that the word apple here refers to the tech company and not the fruit. So in this slide, you can see how transformers can use the big data technologies. So we have the parallelization. The parallelization is equivalent in it's we use parallelization into things. So the first thing is the model parallelism. Transformers can be parallelized across multiple devices or GPU during training, and we have also the data parallelism. Large data sets can be divided across multiple processing units, and the model is trained on different subsets simultaneously. We have also the distributed training. So big data framework like Horovod, along with distributed versions of popular deep learning libraries like TensorFlow and PyTorch, allow for distributed training across multiple nodes or machines. We have also inference at scale. After training, transformers can be deployed for inference at scale. So big data technologies like Apache Kafka or Kubernetes can be integrated with model serving systems to handle large-scale real-time inference requests. We have also data pipelines. So big data processing frameworks like Apache Beam can be used to design and execute data processing pipelines. These pipelines can include data cleaning, feature extraction, and other pre-processing steps before feeding data into the transformer. And that's it. And thank you for your attention.